It's time for Maths with Mr. Thomas.
I see you shiver with Antissa. Chapter 6, Lesson 12. This is the review lesson for sequences and series. We have made it to the end. Well done. High five. So, just like all the other review lessons, this does not include every slide and every example. It is just me going over the key points from the previous 11 lessons. You may wish to just look at this before an exam, a test, just to make sure there is nothing you have forgotten. Anything you're unsure of, look back to the individual lessons where I will explain everything in a lot more detail and you will see more examples. So what was this chapter all about? Well, we started off ages ago with sigma notation. Sigma, it's one of the letters of the Greek alphabet, and we use it in maths as a short way of writing the sum of terms that follow a pattern. A lot of the time it's written like this. What this means is it's the sum of f of k. But what you're going to do is you're going to sub in different values for k. So you're going to be subbing in here, it says k equals a, so you'd be subbing in whatever a is. Then you'd be subbing in the number above that, then the number above that, then the number above that. You're going to be adding all these different parts together and you'd be going up to this value at the top. With some examples to show you what that means. Well, because you've got 1 squared plus 2 squared plus 3 squared plus all the way up to n squared, you can see you're taking a value and you're squaring it. You're taking the value above that and you're squaring it. The value above that, you're squaring it all the way up to n squared. So the way you would write that is the sum of, you're taking a value, call that k, and you're squaring it. The value you're starting with is 1, so which is why it says k equals 1. That's what you start with. Then you would have 2, then 3, all the way up to n. So this here is n, that is where you finish. So the sum of k squared going from 1 to n means you'd have 1 squared, then 2 squared, then 3 squared, 4 squared, 5 squared, all the way up to whatever n is. There are plenty of examples like that, but you have to evaluate the likes of this. So here you've got the sum of 2k plus 1 going from k equals 1 up to 3. So what do? Well, you write down 2k plus 1, but you swap the k with the value you're starting with. So you swap k with 1, so it's 2 times 1 plus 1. Then you add on whatever you have when you sub in the value above that. So after 1 you've got 2, so you'd sub in 2 in place of k, so it's 2 times 2 plus 1. Then you would sub in the value above that, which is 3, so it's 2 times 3 plus 1. But you have to pay close attention to where you stop. We're stopping at 3, so that will be the last one you sub in. Work that out then, that gives you 3 at 5 and 7, so in this example, it's 15. Example 5 here, again you can see I'm missing examples out. If you're unsure, if you want more examples, look back to the individual lessons. Here we're evaluating the sum of 3k squared take away 7 going from k equals 2 up to 5. So first of all we take 3k squared take away 7 and you sub in 2. You sub that in there, so it's 3 times 2 squared take away 7. Then you sub in the value above that, sub in 3. Stick that in, so it's 3 times 3 squared take away 7. Then the value above that, so it's 3 times 4 squared take away 7. Then 3 times 5 squared take away 7. And again, this shows you where you start. The first value you sub in is 2. Then you sub in the next, and you go up to this value at the top, which is 5. So you'd sub that in. Simplify that. This bracket works out to be 5. This one works out to be 20. This is 41. This is 68, giving you a grand total of 134. After that, we went on to lesson 2, which was the sum of a series with partial fractions. Yeah! I also put in here the difference between a sequence and a series. Remember, a sequence is a list of numbers in a definite order, and a series is just the sum of those terms. Partial fractions can be used to find the sum of a certain series. So with this example here, we had to first of all express this fraction in partial fractions, which is when you take the denominator, you factorize it, so you have distinct linear factors. Here we've got the distinct linear factor, so you can rewrite that as something over 2k plus 1 plus something over 2k minus 1. The somethings just write as a and b. Here, this fraction here is over 2k plus 1, but you're wanting the 2k plus 1, 2k minus 1 in order to get the 4k squared take away 1. So you're missing the 2k take away 1, so multiply the top and the bottom by that. This one here, the fraction's over 2k minus 1, you're missing 2k plus 1, so multiply numerator and denominator by 2k plus 1. After that, you'll see the denominators are the same, therefore you can add the numerators. So a bracket 2k take away 1 plus b bracket 2k plus 1. Woo! If you do that, you'll see then that the denominators are the same. This 2k plus 1, 2k minus 1, if you multiply it out, is the same as the 4k squared take away 1. So, multiply both sides by that, or cancel your denominators. Really, the numerators would also be equal. So this 1 would equal this top line here. You need to find the values of a and b, so pick certain values of k that will eliminate either a or b. If k was equal to 1/2, you'd have 2 times a half take away 1, which is 0, so you'd have 0a. If you've got 0a, it lets you find the value of b, which works out to be 1/2. Let k equal -1/2, because -1/2 times 2, add 1 is 0, so you've got 0b, that's eliminating b, allowing you to find the value of a. If you want more with partial fractions, look back to the very first chapter. Let you find the values of a and b. A was over 2k plus 1, so replace a with the -1/2. B was over 2k minus 1, so replace that as well. Don't write it like that with a fraction within the fraction, it just looks pure mental. All you have to do is just move the very bottom, the 2 down to the very bottom, and this 2 to the very bottom as well. Yeah. If you do that, I'm just going to write the positive one first and put the negative one after it. So as you're expressing it in partial fractions, and the whole point in doing that is to find the sum of a series. We can then apply the knowledge of partial fractions. We can apply what we just worked out in the last page to the likes of this question here. We're wanting the sum of 1 over 4k squared take away 1, going from k equals 1 all the way up to n. So it means we're going to be subbing in 1, then 2, then 3, then 4, then 5, then 6, blah, 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 all the way up to n. But use that part A, use this as partial fractions. If you write that in partial fractions, this is what you have. So if you write it in partial fractions and then sub in 1, then you get 1 over 2 times 1, take away 1 over 2 times 3. Then you would sub in the next value, so after 1 you sub in 2, so it gives you plus 1 over 2 times 3, take away 1 over 2 times 5. Then you sub in when k is 3, so you get 1 over 2 times 5, take away 1 over 2 times 7. But the reason you do that is if it's written in partial fractions, you can easily see that you'll be taking away this 1 over 2 times 3, and then immediately you're adding it back on, so these will cancel. So the last term will always cancel with the first term when you sub in the next value. So this one here cancels with the first one. The last one will then cancel with the first. And if you keep on going, you're going to be subbing in n. So if you sub in n, well, you would end up with the first term cancelling with the term before that. So whatever was before that, you would cancel, and you'd be left with this takeaway 1 over 2n, 2 bracket 2n plus 1. And that is all you would have. So this 1 over 2 at the start, you still have, and the very, very last term there, you also have that. Part C, evaluate this 1 over 4k squared take away 1, going from k equals 1 all the way up to infinity. When it's going up to infinity, you're wanting to be thinking about limits. So what happens as k gets bigger and bigger and bigger and bigger and bigger and bigger and bigger? Well, you will see that you're really taking this value of n. You've got the 1 over 4k squared take away 1, going from k equals 1 all the way up to n, but n is going to become absolutely humongous. So really you're thinking as n approaches infinity, what will happen? Again, use your previous answer. This worked out to be a half take away 1 over 2 bracket 2n plus 1. Think about the fraction here. You're replacing n with 1, then 2, then 3, and you're replacing n with a bigger and bigger and bigger number. If you do that, you're going to be dividing 1 by a bigger and bigger number. If you've got one cake and you divide it by more and more people, then eventually the bit they get will get smaller and smaller and smaller and smaller and smaller and smaller. And it'll tend towards, it'll get closer and closer towards 0. So really, it just becomes insignificant. So you're going to end up with a half takeaway, some number that's exceptionally close to 0. So you may as well just call that 0. So you'd be left with 1/2. After the sum of a series with partial fractions, we looked at the method of differences, which is very similar. You are going down the same route as partial fractions with the whole idea that you can cancel. So an algebraic identity can be used to find the sum of a series, and the method of differences is a tool that takes advantage of when terms in a series can cancel, the way we just saw. So you're wanting to show that this is equal to k bracket k plus 1. Well, first of all you've got to do is take out common factors. So we take out a common factor of a third, take out a common factor of k, and take out a common factor of k plus 1. What we're going to be left with then, you can simplify, so that's easily showing that the left-hand side equals the right-hand side. The whole point in doing that is we can show that when we take the sum of the k bracket k plus 1, going from k equals 1 all the way up to n, we need to show it's equal to this. And this is where you use that method of differences, because you're going to be rewriting that as you've got something, take away something. So you sub in k equals 1 in here, sub in k equals 1 in here, so you end up with a third, 1, 2, 3, take away a third, 0, 1, 2. Then you'd be subbing in 2 in here, and 2 in here. If you do that, what you will notice once again is that the first term is always going to cancel on the next line. You're going to end up taking it away. So again, the first term here is going to cancel when you take that away on the next line. This one here would then cancel with whatever you have here. This one here, whatever you have first, will then cancel with the next one. And really all that it leaves you with, you can see, is leaving you with this here, which is going to be take away a third times 0 times 1 times 2, which just works out to be 0. But it's leaving you with this very last one here, a third n plus 1 n plus 2, which is the same as the n plus 1 n plus 2 over 3. So really all you're wanting to do is you're wanting to use what you normally get for part A, sub in the value of k, expand it a little, keep going and seeing what cancels. Once you see what cancels, see what you are left with. In this case, it's the third n plus 1, n plus 2, which you can rewrite as that. A lot of the time there will be a part C for these types of questions. Evaluate the sum of the series 1 times 2 plus 2 times 3 plus 3 times 4. Really, you'll see that that follows the pattern that we had in that part A. It's the k plus 1. So you're subbing in 1, then 2, then 3. So it's going to be 1 times 1 above that. So it's 1 times 2. Then you'd have 2 times 1 above that, so 2 times 3. Then 3 times 1 above that. What we know is that for part B, well, we had that result. We know the sum of the k plus 1 going from 1 up to n was equal to this. So all you have to do to evaluate the sum going from 1 to 99, you're replacing n with 99. We then looked at summation formulas. And there are two properties of sigma that we need to know. The first one is if you've got the sum of one function plus another function, going from k equals 1 all the way up to n, well really you're subbing in 1 into both those functions. Then you're subbing in 2, then 3, then 4 all the way up to n. But what you could do is you could take function f and you could put them first, and then you could take the function g and you could put them second. So really you can say you've got the sum of function f going from 1 up to n plus the sum of function g going from 1 to n. So if you're ever taking the sum of two functions, you can split it up. So the sum of the first function plus the sum of the second. So it's just here. First property. Second property is if you're multiplying your function by a constant, such as a, well really if you sub in 1 then 2 all the way up to n, you're going to have a times f of 1 plus a times f of 2 plus a times f of 3. All the a's you could take out, those a common factor. And if you do that, well you've got a times f of 1 plus f of 2 plus f of 3 all the way up to f of n. So that's really the sum of function f of something, going from 1 all the way up to n. Here's just f of k going from k is 1 all the way up to n. But the a is just taken outside. So if you ever have a constant in front of your function, you can just take that outside. These two properties are not given, you just need to know them. What you are given though is just at the bottom here, you are given these three. Woo! They are on the formula sheet. This is talking about if you have the sum of 1 going from k equals 1 all the way up to n, well really you're adding on 1. Then you're adding another 1. Then you're adding another 1. Then another 1 all the way up to n times. So if n was 7, it will be 1, add 1, add 1, add 1, add 1, add 1, add 1, 7 times. So it's just going to be 7. So whatever n is, it's just going to be n. If you're wanting the sum of 2 going from 1 up to n, we'll say n was 3, well you would have 2, that would be the first term. Then you would have 2, that would just be the second term. Then 2, that would just be a third term. Even though you're meant to be subbing in 1, well you can't really do that because it's just a constant that you have. But what you're left with is, as I said, if that was 3, you'd have 3 2's. So in other words, 2n, that's what you would have. These ones are not given on the formula sheet, they're ones you just really have to try and think about. If it's ever the sum of just 1 or the sum of just a number. What you are given is the sum of k. So if you've got the sum of k going from 1 all the way up to n, well, what you're wanting to do with that is work it out, but it's already been done for you. Look at the formula sheet. That is just n bracket n plus 1 over 2. And the sum of k squared is n plus 1, 2n plus 1 over 6. And the sum of k cubed is n squared, n plus 1 squared over 4. And as it says here, this one here is just the sum of k squared. So the n is squared, the n plus 1 is squared, and the 2 is also squared. It's a random wee note. These three are given and you need to know how to use them. For example, if you want the sum of 2k cubed minus 3k going from k is 1 all the way up to n, well, the first thing you could do is you think, right, well, I've got two functions here, so I can split them up. So it's the sum of the first minus the sum of the second. But you've also got constants in front of k, so you can take that outside, sigma. So you've got 2 times the sum of k cubed. Take away 3 times the sum of k, going from 1 up to 10. And the sum of k cubed, well, it's just given here. This here is the sum of k cubed. It's n squared, n plus 1 all squared over 4. N, in this case, is going to be 10, so you're going to have 10 squared. Times, well, 10 add 1 is 11, so that's going to be 11 squared over 4. The sum of k is given here is n plus 1 over 2. K is going to be 10, so you're going to have 10 times 1 above that, which is 11 over 2. So it's going to be 3 times that. Sub them in, work them out, and you get your answer. Remember, look back at the individual lessons if you're wanting it explained in a bit more detail. The sum of k squared going from k is 25 up to 45, what you really have to do for that is always imagine you are starting at 1, because each of these summation formulae always start at 1, from k is 1 all the way up to n, 1 up to n, 1 up to n. So if you want the sum from 25 up to 45, really you're thinking, well, that's the sum from 1 up to 45, but you're taking away when you subbed in 1, then 2, then 3, all the way up to 24. So it's going to be the sum of k squared from 1 to 45, take away the sum of k squared going from k is 1 up to 24. Again, use the formulas here to work that out. K squared is n plus 1, 2n plus 1 over 6. Here, you've got 45, so you're going to have 45 times 1 above that, which is 46, times double it, add 1, you get 91 over 6. And it's the same with the other one as well. So you will get your answer. We then went on to look at arithmetic sequences. Yeah! What is an arithmetic sequence? Well, this and the one here, 1, 3, 5, 7, 9, we are adding the same thing every time. A sequence where we add or subtract the same number each time is known as an arithmetic sequence. Two things you need to know is first term is known as a equals. Here the first term is 1, so you write down a equals 1. Whatever you are going up in is known as the common difference, and you write that as d equals. So for each of these, well, you see the first term is 2, so a is 2. You're going up in 2's, so the common difference, d, is going to be 2. With this one here, you're starting with 8, so a is 8, and because you're subtracting 4 every time, well, you can say that the common difference is negative 4. When d is less than 0, so here d is negative 4, it just means the sequence is decreasing, as you can see there. How do you find a certain term in an arithmetic sequence? Well, you can use this formula. Un, a certain term, is equal to a plus n minus 1d. That is the general formula to find a particular term in an arithmetic sequence. For example, here, if you're asked to find the 25th term of the arithmetic sequence, 2, 6, 10, 14, what I always like to do is write down what I know first of all. So if I know the first term, write it down. If I know the common difference, write it down. If I know the value of n, write it down. So here, the first term is 2, so I've got a is 2. I know the common difference, I'm going up in 4, so I write d is 4. And because I want the 25th term, I know n is equal to 25. So the formula is un equals a plus n minus 1d, but because it's 25th, replace n with 25, so u25 would equal, replace a with 2, replace n with 25, so 25 take away 1, multiply by d, d is 4, and then work that out, and you get 98. Other examples, find the formula for the nth term. So here, we're now going to be subbing in a value of n. We're wanting to have n in our answer. We want a formula for it. This is our arithmetic sequence, 1, 4, 7, 10. Again, start writing down what you know. We know the first term, so we know the value of a. We know it's going up in 3s, so we know d is equal to 3, the common difference. Un equals a plus n minus 1d. Replace a with 1, d with 3, multiply out the brackets, simplify, and that is your formula for un. We then went on to look at the sum of an arithmetic sequence. Remember, a sequence is a certain list of numbers in a certain order, and a series is the sum of those terms. If we have our sequence and we're adding, it is known as a series, and we can find the sum of that series, or the terms of an arithmetic sequence, by using this formula here. The sum of n terms is equal to n over 2, and then in curly brackets 2a plus n minus 1d. What you'll notice is that this a plus n minus 1d is the previous formula that we just learned. It's a good way of remembering them. So example 1 here, find the sum of the first 15 terms of this arithmetic sequence. Again, similar to the last set of examples, the last lesson, write down what you know. So if you know a, write it down. We know a here is 3, it's the first term. We know there's a common difference of 5. We're adding on 5 each time, which makes it an arithmetic sequence. And n, well, how do we know n? Well, read the question. Find the sum of the first 15 terms. So if it's 15 terms, we know n is equal to 15. Woo! We can use that formula then, replace a with 3, d with 5, and n with 15, work it out, and you end up getting 570. Which means if you add 3, add 8, add 13, add 18, add all the way up to the first 15 numbers, you would end up with 570. There are plenty more examples with that. With this one here, find the sum of the arithmetic series. 12 add 19 add 26 add 33 add all the way up to 285. You'll notice with this one we don't know how many terms are in the series, so we have to find that first. Find it by using the previous formula. un equals a plus n minus 1d. And you're using the knowledge that the 285 is the last term. So if you find out what n is for that, you find out how many terms are in the series. Once you know that, you also know a, you also know d, so you can sub them into this formula in order to work out the sum of those terms. We then went on to look at geometric sequences. How are they different? Max, do help us out. Perfect, well done. A geometric sequence, we are not adding the same thing every time, we are multiplying by the same thing every time. So with this one here, 1, 2, 4, 8, 16, you'll see we are multiplying by 2 each time, and when we multiply by the same thing, it is known as a geometric sequence. Again, you've got a equals, a is always your first term. The first term is 1, so a is 1. And there's a common ratio, which is what you're multiplying by every time, and that is 2. The way you can find the common ratio, if you're just given a geometric sequence, we'll take the next term and divide by the previous term. So in other words, do u2 divided by u1, or u3 divided by u2, or u4 divided by u3. Really, you just take un plus 1 and divide by un. That'll give you the common ratio. With these sequences here, we had to work out a and r. A is the first term, that's dead easy, so that's going to be 1, that's 27, that's 1, that's 18. Simple. To work out the common ratio, remember, just take a term and divide it by the previous term. So 4 divided by 1 was 4. It works out no matter which way you do it. 64 divided by 16 is also 4. If you do 1 divided by 3, that's just 1/3. Or 1/9 divided by 1/3, if you want to do that, it's still 1/3. -1 divided by 1 is -1, so that's your common ratio. That's what you're multiplying by each time. And with this one, -12 divided by 18 gives you -2/3. Again, you could, if you're absolutely crazy, do 32 over 9 divided by -16 over 3. And that will give you -2/3 as well. Really, once you know a and r, you can work out the nth term the same way that you'd work out the nth term of an arithmetic sequence, except the formula is different. The formula for a geometric sequence is ar to the n take 1. Yo! So, if you want to work out the 10th term of this geometric sequence, again start writing down what you know. If you know the first term, the common ratio, what the value of n. A is 3, so first term, the common ratio, we'll divide one term by its previous term, so 12 divided by 3 is 4, so that is r. N is 10 because there's 10 terms, and use AR to the n take 1, so U10 would equal AR to the power of 10 take away 1 is 9, replace A and R as well, and that would give you 786,432 for that question. We then looked at the sum of a geometric sequence as well. So your geometric sequence, remember, is when you're multiplying by the same thing every time, and we can work out the sum of a geometric sequence by using one of two formulas. It does not matter which one you use, but it makes it easier arithmetically if A is bigger than 1 to use this formula here. If R is less than 1, use this formula here. So, with these formulas, example 1, find the sum of the first 9 terms of a geometric series, 4 plus 8 plus 16 plus 32. Again, write down what you know. If you know the first term, write it down. If you know the common ratio, well, you can work it out. 8 divided by 4 is 2, so that's your common ratio. That's what you're multiplying by every time. And n is 9 because we want the sum of the first 9 terms. Because r is bigger than 1, r is 2, use this formula here. So a bracket r to the power of n take away 1 over r take away 1. Replace the value of a with 4, r with 2, n with 9, and you get an answer. That answer is going to be the sum of the first 9 terms. Woo! With this example here, evaluate the sum of 0.9 to the power of k, going from k equals 1 all the way up to 20, giving your answer correct to 3 decimal places. First thing to do when you get this is freak out. No, it's not. Don't freak out. All you have to do is think about what it means. Remember, sigma means the sum of. So it's the sum of 0.9 to the power of k. So you've got 0.9 to the power of, and you're starting with 1. So it means 0.9 to the power of 1. Then you're adding on 0.9 to the power of the next number. Well, after 1 is 2, so it's 0.9 to the power of 2. Then you add on 0.9 to the power of the next number, then the next number, then the next, all the way up to the 20th number that you would sub in. So you sub in 1, then 2, all the way up to 20. So you then have 0.9 to the power of 20. Write down what you know. So if you know a, r, or n, write them down. Well, a is the first term, that's 0.9. What are you multiplying by each time? Well, you've got 0.9. Next term is 0.9 times 0.9. So you can see that with the original 0.9, you squared it, you multiplied it by itself. So you know you multiplied by 0.9. That was your first term, it's to the power of 1, that's your second, that's your third. Really, there are 20 terms there in total, so n is going to be 20. Since r is less than 1 this time, you're using this formula at the bottom. And you would then have a bracket 1 minus r to the power of n over 1 minus r, replace a, r, and n, and you'll get your answer. Just make sure if you're asked to give it to 3 decimal places that you do that, and you'll get a pat on the back. Well done. There are some of the harder questions with this as well, so find the least number of terms of the geometric series, 4 plus 12 plus 36 plus 108, that must add to give a sum exceeding 1 million. With this one here, again, start off writing down what you know. So we know the value of a, we can work out the common ratio, we're just multiplying by 3 each time, 12 divided by 4 is 3, but n, we don't know how many terms we will have. But what we do know is that we have to add them so we get some number, some total that's going to exceed 1 million. Start off with that formula. If you can simplify it, then do that. Sum in the value of a and r. You're doing that. That, therefore, is going to be your summation formula for this. But because you're wanting something to exceed 1 million, well, set it equal to 1 million. Don't start dealing with bigger than or less than signs or anything like that. Set it equal to 1 million, and then find the value of n that will make it equal to 1 million. So you've got this 2 bracket 3 to the power of n take away 1 equals 1 million. Rearrange that to get n. Well, if you get down to this stage, 3 to the power of n equals 500,000 and 1. Then in order to solve that, you need to take logs because it's this index you're wanting to find. In advanced higher, it's really just natural logs that you need, so just take natural logs of both sides. The point in doing that is you can move n down. Come on, move down. There we go. So you've got n times ln3 equals ln 500,000 and 1. Rearrange that to get the value of n, plug that into the calculator, and that gives you 11.94. That means then it's the 11.94th term that will give you 1 million. But that makes no sense. It means that it's going to be the 12th term that you would add on, which would give a sum to exceed 1 million. Because if you think about it, you're going to have one term, then you're going to have the second number, then the third number. There is no 11.94th number. It makes no sense. But it shows you that it will reach 1 million between the 11th and the 12th number. So if you get the sum of 11 numbers, when you add on the sum of 12, it'll take you over 1 million. So because it's between that, then you'll have to round up the way. So the 12 terms will be the first that will give you a sum that exceeds 1 million. We then went on to look at the sum to infinity. And what's this talking about? Well, you can see for this Geometric sequence, if you add all the terms together, well, say you add the first 5 terms, you get 31. If we extended it slightly and added the first 10 terms, we'd get 1023. If we kept extending it and adding 20 terms, we get over 1 million. Really, you can see that the sum of the first n terms just increases without a limit. But if you look at this geometric sequence here, really you're dividing by 2 every time. So we've got half, then we've got the quarter, then 1/8, then 1/16. Well, you can see that if you add 5 terms together, you get 0.9375. If you extend it and add 10 terms, well, you get 0.998. If you added 20 terms, you get 0.999. Really, for this one here, it's approaching a limit, and that limit is 1. So the more terms you add, the closer and closer it gets to 1. So we say then that the geometric sequence has a sum to infinity of 1. And you write it with a capital S and then the wee infinity sign, and that would equal 1. The series will have a sum to infinity if the common ratio is between -1 and 1. So this is similar to what you learned in Advanced Higher with your recurrence relations. So if R, your common ratio, is between -1 and 1, there is a sum to infinity. It exists. And you work it out using this formula. The sum to infinity equals A, remember the first term, over 1 take away R. But remember, it's only if R is between -1 and 1. We looked at some examples of that. So this one here explaining why the geometric series 27 plus 18 plus 12 plus blah, 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 has a sum to infinity and find its value. Well, A is your first term, that's 27. The common ratio to work that out, take a term and divide it by the previous term. So 18 divided by 27 works out to be 2/3 if you simplify it. R is 2/3, that's between -1 and 1, so the geometric series will have a sum to infinity, and you can work it out using that formula. Sum to infinity equals A over 1 take away R, which is going to be 27 over 1 take away 2/3. Works out to be 81, so that will be your sum to infinity. After we looked at sum to infinity, we went on to look at the last part of sequences and series, which was the Maclaurin series. What is that all about? Well, it kind of uses that knowledge of sum to infinity. Here, the geometric series 1 plus x squared, you can see that you're multiplying by x each time. Because you're multiplying by x each time, that is your common ratio. Meaning if you sub that into the formula for the sum to infinity, you would end up with a sum to infinity of 1 over 1 take away x. But remember, it's only when the common ratio is between -1 and 1. So in this case, it's only when x is between -1 and 1. So you can say the 1 plus x squared plus x cubed and so on would equal 1 over 1 take away x. If you rewrite this, you can rewrite that as 1 take away x to the power of -1. That there is your function, and really is showing you that the function can be expressed as an infinite series of that form. Some constant plus a constant times x plus a constant times x squared plus a constant times x cubed, where a0, a1, a2, a3 are all constants. And really, in general, any function can be expressed as the sum of an infinite series. This is known as your power series, or your Maclaurin series, named after the Scottish mathematician Colin Maclaurin. It's important to know, though, that the power series, or Maclaurin series, only converge for certain values of x. To work out the values of these constants, what you need to do is replace x with 0. So if we worked out f of 0, then that would give us a0 plus a load of zeros. So it tells us that a0 is equal to f of 0. In order to work out a1, we have to differentiate and then sub in 0. So if you differentiate that, sub in 0, then a1 is equal to just f dash 0. To work out a2, we differentiate again. Really, what we have to do when you use the Maclaurin series is you differentiate, sub in 0, differentiate, sub in 0, differentiate, sub in 0, and you keep doing that. This formula here is given in the exam, it's on the formula sheet, and it's saying that the function is, if you express it as a Maclaurin series, is f of 0 plus f dash 0 times x plus f double dash 0 over 2 factorial times x squared plus, and so on. It follows that pattern. So really, when you get to the examples, what you have to do is you differentiate and then sub in 0, and then you can sub the values in to the formula that you are given. With this one here, we had f of x equals e to the power of 2x. We want to go up to and including the term in x to the power of 4. Because you've got an x to the power of 4, we can see that when it's x to the power of 4, it's the fourth derivative. So you start off with e to the power of 2x, differentiate that, differentiate it again and again and again, so you get the fourth derivative. Then work out f of 0, f dash 0, f double dash 0, and so on. Work out these values. After you work them out, well, you just replace f of 0 with what you found it to be. That's 1, so sub it in. Here you had f dash 0 times x, so that's 2 times x. Here it was 4 over 2 factorial. Remember, 2 factorial is 2 times 1, so it's 2. Multiplied by the x squared. 3 factorials, 3 times 2 times 1, 4 factorial, 4 times 3 times 2 times 1. So replacing them with 6 and 24. Basically, sum it all in, simplify it, and that is what you'll get. So that is you expressing your function as an infinite series. We had quite a few examples with that. They did start to get slightly trickier. So with this one here, it's not so easy to differentiate, but it's the same rules. You're doing the same thing every time. You have to differentiate this, so write it as the power of a half, bring the half down, take 1 off the half, keep the brackets as they are, multiply by the derivative. Do the same thing again, just follow those steps. Remember, once you've done that, you want to work out f of 0, f dash 0, f double dash 0, and so on. Work them out and get the values. After you do that, then you're wanting to sub it into this formula. So f of x in this case is the square root of 1 plus 4x, and then replace f of 0 with 1, replace f dash 0 with 2, replace all of these, simplify it, and again you're expressing that function as an infinite series. Woo! To finish off this chapter, I split the Maclaurin series lessons in 2. So I had the first one just with a brief explanation and then some examples, and the second one was some of the trickier questions. So there was like a part B. These are the types of questions that would probably pop up in the exam. First part's probably going to be easy enough. Second part's a bit harder and you've got to think about it. So these ones here are quite common. With this, you had to obtain the Maclaurin series for f of x equals e to the power of x sine x. You know, for the Maclaurin series you have to differentiate, but because you have the sum of two functions, you need to use the product rule. If you do that, then you do u dash v plus uv dash and you'll get an answer. Make sure you factorise that answer. It makes the next bit easier because again you're going to have to differentiate it, and to differentiate it you use the product rule again. Use the product rule again, take out common factors, or in this case I'd maybe just multiply out the brackets and simplify. That's what I did here and I got that. But again, it's a product of two functions, so use the product rule. Work that out, simplify it, again, product rule, multiply it out, simplify it. This is what you get. Really, you're being tested on knowing to differentiate, you're being tested on the product rule, simplifying, and so on. You know, once you do that though, you're going to be replacing x with 0, so work out f of 0, f dash 0. If you do that, you get these values. Really, it's the same thing though as the questions in the previous lesson. All that you're doing is just differentiating something that's slightly trickier, and then evaluating it again when it's slightly trickier. So with this here, you're replacing f of 0 again with 0, f dash 0 with 1. Really, you differentiate, replace x with 0, and sub those values into the formula. Just be careful, you might be asked to find up to the term with x to the power of 4. Sometimes though, like in this case, it works out to be 0. You'd have 0 x to the power of 4. In that case, you don't need to write it, but you do need to have the working behind that to show that you worked out the fourth derivative, you evaluated that. So be careful, it's sometimes a trick question, kind of. For part B, this is the bit that you need to think about. So you have to work out the Maclaurin series for e to the power of 2x sine 2x. With this one here, it's only worth 1 mark, possibly 2 marks. You don't have to do an awful lot. You don't have to do the whole thing again and differentiate it using the product rule. You'd be there forever. What you need to do is use your previous answer. This is the previous answer here, e to the power of x times sine x equals x plus x squared plus a third x cubed. Really what you're doing though is for function g, you're replacing the x here with 2x. Again, instead of sine x, you're replacing x with 2x. So all you have to do is, because on the left hand side you're replacing x with 2x, on the right hand side you would do that as well. So instead of x, you've got 2x. Instead of x squared, you've got 2x all squared. And the same here. Multiply the brackets, simplify it, and that's what you would get. Again, similar to the last part, you'll be asked to express it up to and including the determinant x to the power of 4, but the coefficient for that was still 0. But for part A, we had the working behind that to show it would be 0. There were quite a few examples. This one here was probably one of the easier-ish examples, but there's a tricky part in it. The tricky part is when you differentiate your sine squared x. Well, first of all, you think about it as sine x all squared. Differentiate that, the 2 comes down, the brackets stay as they are. Decrease the power by 1, multiply by the derivative, so you get 2 sine x cos x. What lots of people do with that one is they then use the product rule. And you can use the product rule, it's absolutely fine, but it'll take you a lot longer. Try to think about your trig identities. 2 sine x cos x is equal to sine 2x. If you rewrite it as that, it makes it a lot easier to differentiate. So that question there was thrown in because it's a trickier question, because you need to identify that the 2 sine x cos x is equal to that. It makes this question quite easy. If you want to try it with product rule, feel free, give yourself 3 weeks and you still get the same answer. It doesn't really matter how you are doing it, but look, see if you make it easier for yourself. You're still going to use the formula for the Maclaurin series, and you're still subbing in 0 in place of x for f of 0, f dash 0, f double dash 0, and so on. If you do that, again, you can still express it as an infinite series. Part B for this, well, we just worked out a series for sine squared x. We're wanting one for sine cos cubed x, and to do that we need to use this knowledge that we learned about years ago. Sine squared x plus cos squared x is 1, so cos squared x is the same as 1 take away sine squared x. We just worked out what sine squared x is equal to, so we can sub that in. Again, this is part B. It's only worth 1 or 2 marks. There's normally a tricky bit that you need to think about. How could you get it? Well, this is what you would do in this case. That is it for the review lesson. Remember, there are plenty more examples. There's a lot more of an explanation if you look back to the individual lessons. Best of luck with this chapter. Have fun. Bye. Patience.